Hello and welcome to another one of D's ADD videos. Today we're going to look at some intermediate examples of electron configuration. Alright, let's start out with titanium. Titanium is here in the D block. It's on the fourth row. So when we're doing our filling of electrons, we could either A, use the periodic table. So it'd be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d2, okay? Or we could use a diagonalization method. Now we'll write it out, don't worry. So if we're using diagonalization, it would be 22 electrons, I believe is what it was. So 1s2, 2s2, 2p6, 3s2. 3p6, 4s2, then 3d2. Alright? Either way works. So let's see it in action. So I'm going to show you the actual diagonalization of this one. I personally prefer the periodic table. If you understand that each segment is associated with a subshell, it's pretty straightforward. And then it's actually it goes diagonal, diagonal, diagonal. So in this case it would be 3p6, then 4s2. Then we would go into the 3d2, and that should add up to 22. So there's 4, 10, 12, 18, 20, 22. Okay? So if you were to write it out, it would look like this. And you can see why the shorthand notation is preferable, because if you did the shorthand notation, the noble gas in the prior row would be argon, and then you could do the valence shell, the outermost shell. So that would be argon, noble, and then we would have the 4s2, then the 3d2 left over. Much easier to write. Shorthand notation. Okay, arsenic, next candidate. You know what? We don't have room for arsenic, so I'm going to erase you, and we'll come back to arsenic here in a little bit. Can I squeeze them? No. I'm not over there. Yeah, we can do arsenic over here. Arsenic on the periodic table. Arsenic is what they use in rat poison. It's bad stuff. So we're way over here. So using the periodic table, you should realize it's 1s2, 2s2, 2p6, excuse me, 3s2, 3p6, 4s2, 3d10, and then 4s3. Okay? Using the diagonalization method, it would be 1s2, 2s2, 2p6, 3s2, 3p6, then it's 4s2, 3, because we subtract 1 from the quantum number for the D subshell, and if you remember, the D was completely full. And then we go back to 4 for the P. And how many of those were there? Let's see, let's go back to the periodic table. So I did the 3D, and then we were at 4p3. 4p3. Okay? Again, using the shorthand notation would be preferable here, because all you have to do is argon and then this outermost valence shell. So if I did the shorthand notation, it would be argon again, and then it would be the valence means outermost shell. Okay, that's your shorthand. Okay, let's see. We can do tungsten. I'm just going to do the shorthand from now on, unless they ask you to do the long notation. Go ahead and use the shorthand. So tungsten, where is good old tungsten? Right here. Okay, so we have 74 electrons. Are you really wanting to write all those out? No. So what you do is you go to xenon, the noble gas on the row prior to tungsten, W. So we would write xenon, and then we would have what? Let's look at our diagonalization method. So let's go ahead and write the xenon. And then after we do that, we're on what row? We're on the 6th row. So let's see what happens when we do the 6th row. 6s2 is what we go to. So when I'm filling, it would go to the 6s2, then the 4f would get filled, and then the 5d would get filled, and then we'd go to the 6p. But actually, tungsten is in the 5d. All right? So 6s2, 4f14, and 5d, however many we got to go out. So let's look at that. So we got the 6s2, the 5f would then get filled. Actually, sorry, it'd be the 4f because it's 2 less for the f orbital. So the quantum number of 6 gets subtracted by 2 to give you 4f14. Then after that, we go into the 5d, because you subtract 1 from the d, and you get this guy here, tungsten. I guess it would borrow 1 from the S subshell. I hadn't intended for that to happen on this one, so typically copper and molybdenum do that. I guess this would too if we follow the rules. So we had 6s2, 4f. I'm following that diagonalization. So 6s2, then the 4f14, and then the 5ds. Oops. So the borrowing example is supposed to actually be the chromium, but what we're saying here is the d orbital will tend to borrow an electron from the s orbital and put it into the d to make it either half full or completely full. So if that were to occur in this scenario, you would have 6s1, 4f14, and 5d5, which is a lot more stable. Okay? So the same concept would happen with chromium here, except for it's a lot further up. We would have the argon, then the 4s2, and 3d4 if we use the normal rules, but we just learned that we would borrow an electron from the s to make this 4 a 5 and make it halfway full for the d subshell. So in this case it's going to be again argon, then 4s2, or actually 4s1, sorry, and then 3d5 for chromium. All right, so you should be able to do these pretty easily after you practice enough of them. Once you get the hang of it, you can use the shorthand notations a lot quicker to deal with that, okay? But just in case they do ask for the long explicit way of doing it, make sure you know the diagonalization rule or understand how to do it using the periodic table. There will be one more advanced examples video that I want you to check out that has ions. Ions lose their electrons first from the s, and then just check out that video. More importantly, practice, practice, practice. Thank you and have a nice day.